All right, in this video, we're going to look at an example of logistic regression. So we're going to focus more on interpretation of specific coefficients, as well as how we make predictions for the likelihood of a particular outcome given some predictor information that we input into the model. So the last video, we kind of did more of an overview of what is logistic regression. Now we're going to get into more of the details of these kinds of calculations to the extent that we care about them in this class. So again, we're not really going to delve too much into the method of logistic regression. We're not really unpacking how we get these coefficients. So we're just saying that this is what logistic regression is. This is when we use it, and we can use R or some other software to fit a logistic regression model. And then we're going to jump back in for the interpretation side of, we have this model, what does it mean? How would I make predictions from it? Okay, so if we take this original model exactly as it is, it's honestly not the easiest thing to interpret. We can though, we can start from that, and then we're going to kind of work through some new some algebraic manipulation to see how we can eventually get to a prediction of P itself, as opposed to a prediction of the log odds or just the odds of being biologically male in this case. So remember that P right here, this represents the likelihood, the probability of being the outcome that's coded 1 in our example. In this case, we coded biologically male as 1. You might be doing a different case where it's some other question. We have other outcomes. Maybe it's survive or die are the two outcomes, and maybe we coded survive as the one case, or the one code in that case. So just kind of keep that in mind, that P is the probability of the outcome we coded to 1 actually occurring based on the predictor information that we inputted. All right, so if we want to interpret this coefficient literally, it represents how a 1 unit increase in our predictor here, which is height, will affect the log odds of being that case, that outcome coded to 1, which is biologically male. So then we could say for every 1 unit increase in height, the log odds of being biologically male will increase by 0.448. And I don't know about you, but that is not the most meaningful statement that I've ever read. I don't think about log odds of an outcome as like, oh yeah, the log odds, it's not the most intuitive measure to me. Which is why we're going to do some algebraic manipulation to kind of get this into a form that's more clearly linked to the response. It's more clearly linked to just the probability, or we could also call it the likelihood of being biologically male. So we're going to first start with one step, and that's just turning the log odds into the odds, because that's at least a little bit more familiar. We've talked about the odds, or the risk for that matter, as being a scale from 0 to positive infinity, where 1 means equally likely. More than 1 means that one category is more likely than the other. I guess 0 to 1 means the same thing, but the category of interest, the category that we have specified in this question, when the odds are above 1, it means that category is more likely. When the odds are below 1, it means that category is less likely. So at least that's something familiar. So to get to that form, what we need to do is take the log off of this side. And if you remember algebra, you know that we can do the same operation to both sides and still preserve the equality of this equation. So if I take e to the log of p over 1 minus p, that's just going to be p over 1 minus p, because e is going to be the inverse operation of a natural log. So e to the natural log just cancels out, and it just becomes p over 1 minus p. That may or may not be familiar. I'm guessing a lot of you've probably done this before. Some of you, this might feel like, ooh, like what are you talking about? And that's okay. It's okay if you don't understand the math behind the log and natural log and e and all that. As long as you just know that's what we're doing here, that you can kind of follow this this change, and we can take e to this other side, and that's how we're getting there. So yeah, to preserve that equality, we're going to take e of both sides. This simplifies to just the odds of being biologically male. And now we have e to this side of the equation, which algebraically we can just break up into two terms, e to this term times e to that term. Which means, sorry, one more thing. And let's also observe here that e to the 0.448, so if I take e to the 0.448 on my calculator, I'm going to get 1.565. So that means that for every 1 unit increase in height, for every 1 unit increase in this x value right here, the odds of being a biological male will be multiplied by e to the 0.448. So if I'm comparing two people of the same height, if I'm comparing two people where one person is 1 inch taller than the other person, then we would say that the odds of that taller person being biologically male will be multiplied by 1.565 compared to the odds of the other one. So then it becomes kind of this form, this representation of how the odds are changing as height increases by 1 inch. But the thing is, this odds increase is not linear, right? It's not just some additive value for every height like it was when we were doing linear regression before. Because actually what's going on is the change in odds, the change in probability as well, is not a line here, but instead it's going up less and less as I increase height. So if you want to think about it that way in terms of the probability, this is not just an additive increase in likelihood as height goes up. And for the same reason, it's not an additive increase in the odds for every 1 unit increase in the predictor here. So that's why it's actually in the form of a multiplicative change in comparison to somebody of a 1 unit smaller predictor value. Okay, so again, still a little bit complicated, but hopefully maybe some of this makes sense, even if all of it doesn't make sense, and that's probably okay. Okay, so let's go ahead and just use an actual example where we have an actual value to plug in so we can see how this worked and make an interpretation. So let's say that we had somebody who's 71 inches tall. We probably know up front that their likelihood of being biologically male is probably higher than biologically female. It's certainly not 100%, but I would guess it is closer to 1 than it is closer to 0. So based on this model, we can plug in somebody who's 71 inches tall into this equation. I'm going to solve the right side of this equation first. And then I'm going to take e to both sides, and I'm going to get p over 1 minus p equals e to this expression that we found on the right side of the equation. And I can see that my prediction for the odds of that person being biologically male is 5.302. So we would interpret this as meaning the odds of a 71-inch person being a biological male are estimated to be 5.302 to 1, right? So that means that their odds of being biologically male are about 5 times that of their odds of being biologically female. So, that's kind of cool. And the fact that it's greater than 1 means that their likelihood of being biologically male is higher. So again, we might kind of make this observation that odds is still kind of weird. Like, why can't we just report this as the probability? Like, our estimated probability that they are biologically male is some value. And so that's going to be the next step that we do. To turn this into the probability, to solve for this actual p instead of the p over 1 minus p, we can do a simple kind of algebraic trick here. We can just take the odds plus 1. We can take the odds divided by the odds plus 1. So now we can break down the algebra, so you might be just dying to do this if you enjoy math. I'm not going to do it here because it's just not important for our class. But if you want to do it as a challenge, you can kind of figure out why does this change do this if you want to kind of solve for p up here. But for now, all we care about is this is a trick that we can do. Take the odds divided by the odds plus 1, and that's going to solve for the probability. So finally, we get to the probability of a 71-inch person being a biological male is estimated to be 84.13%. So that's a very straightforward value. One more observation that we'll make about the hypothesis test that shows up on this output. So notice that we do still get a hypothesis test result for height, being 0.00345 as the p-value. That's pretty low. We don't have a whole lot of people, meaning that like in order to get a low p-value for a small sample, there's probably going to be a pretty big predictive contribution from this predictor. So just kind of an observation there. But yeah, we get a pretty low p-value, meaning that we're quite confident. We're very confident that height actually has some predictive power in classifying some of these biological sects. So what's the null hypothesis we are testing, and what should we conclude? The null hypothesis is going to be that height is not a predictor of biological sex. This would be how I'd write it in words. If I'm thinking about what it means in symbols, it means that this coefficient is actually 0. That if I had all the biological males and biological females in the world, and I looked at their height, and then I looked at their sex, that I would find no correlation, and therefore the coefficient of this model for the height predictor should just be 0, if that's the case, meaning that there is no value added by knowing someone's height in predicting their biological sex. So I'll kind of put in parentheses beta 1 equals 0. That's just kind of a side note that if you think about the null hypothesis, is that something equals something. And typically it's that something equals 0. And so that's where that kind of relates, is that this coefficient would be 0 if the null hypothesis were true. The alternative would be that height is a predictor of biological sex. All right. So the beta coefficient is correctly some value not equal to 0. We obviously observed a coefficient that's not equal to 0. We observed 0.488. And so the question we're asking is, well, is this just some random chance correlation that we're seeing that, by virtue of taking a sample, we're not going to see exactly 0 correlation. We're probably going to see at least a little bit of correlation by random chance. So the question we're trying to figure out is, could this just be attributed to random chance? Or is this enough to say, yes, height is actually predicting biological sex, that it is actually contributing to the model more than could happen by random chance with this sample of results. Since our p-value is quite low, so p-value equals 0.00345, that means that we're very confident that we have something here. That if the null were true, we would see this much correlation, we would see this larger coefficient by random chance less than 1% of the time. It would be 0.345% of the time. That's quite low, and suggesting that we have some very strong evidence here that there is something here with height as a predictor, and that this isn't just some random chance correlation that we happen to observe with this sample. All right, this is a good place for you to practice your mathematical calculation to see how well you understood some of this stuff that we did. So I'd encourage you to pause the video for a second and see if you can solve what are the odds of a 65-inch person being a biological male, and then secondly, what is the estimated probability of a 65-inch person being a biological female? So notice that I did switch this up. So you might have to think about, well, how do I find the other category? So that would be a really good test to see how well you understand what we just did. But I'd encourage you to pause for a second. Otherwise, I will keep going here and solve each of these. Okay, so the estimated odds of a 65-inch person. So I'm going to take this equation. So it's going to be the log of p over 1 minus p equals that negative 32.98 plus 0.448. Oop, is it 488? It's 488, I guess. Yes, okay. I don't know why in my head I thought it was 448. Okay, 488 times this height of 65. Okay. So I'm going to solve the right side of this first because that will be the easier part. And I get negative 1.26 for the right side of this equation. So that means that my log odds are negative 1.26. So then what I can do is I can take the e of both sides. So then I'm going to get p over 1 minus p equals e to the negative 1.26. And so if I complete that calculation, I'm going to get 0.28365. I guess, I don't know how many decimals I should really report here. 28365. So that means that if I have somebody who's 65 inches tall, I would estimate the likelihood of them being biologically male to be about 28.36. Or I'm sorry, these are not the probability. I got so confused there. This is the odds. The odds of them being biologically male are 0.28365. And notice here that this is a value less than 1, meaning that the odds are in favor of them being female. So I should probably add 0.28365 to 1, meaning that their odds are probably much better to be female, given that this is their height. But again, it's still very possible for this person to be male. It's not that unusual, but the odds favor female more than male, given only this information about their height. All right, what is the estimated probability of a 65-inch person being a biological female? All right, so we can use this information now to solve for the probability. And if you might remember this trick, we can take the odds plus 1, odds divided by odds plus 1 to turn this into a probability. But that would work if you're finding the probability of them being biologically male. But if you remember that the probabilities for each category should add up to 1, I can do that and then just take 1 minus that value to get the probability for female in this case. So I'm going to do 0.28365 divided by 1.28365 and solve this value. And I get about 0.22, we'll just say about 0.221 is what that kind of rounds to. And this would be the probability of biological female, right? So this is, biological male. Biological male. So then 1 minus 0.221 is going to be about 0.779. And this is going to be the probability of biological female. Right? So again, what we're noticing is that, well, we can solve for the probability of them being biologically male using what we've done so far. And then we just take advantage of the fact that their probability of being biological female, if we're treating this as a binary variable where everyone's getting sorted to one of these categories, again, I know we could talk biologically of whether that's appropriate and whether, like how many folks may not be exactly assigned to a biological sex at birth due to, some of the rare but certainly possible things that can happen. But if everyone is sorted to one of these two categories, then we would just take 1 minus that probability to get the likelihood of being sorted to the other category in this case. So yeah, that would be that calculation if we wanted to find the other category probability. Okay. And then I'm just going to make a really quick word here about multiple logistic regression. So just kind of a mention here that we can do this with more predictors as well. So we're not just limited to only having one predictor with logistic regression. We can do this with as many predictors as we want. I'll also just kind of mention here that if we're doing this in the context of biostatistics with medical related conditions, we often call these predictors biomarkers. or prognostic indicators sometimes, meaning that they are kind of predictors of a particular condition. So maybe I want to know the likelihood that somebody developing breast cancer based on certain factors that I know about that person. Maybe I have family history of breast cancer as a predictor. Maybe I have their weight. Maybe I have some kind of hormone level as predictors, right? Well, then I can use that to kind of model the likelihood that they are going to develop breast cancer or not. Like, so if you think about it realistically, either they are or they're not. You know, like the true outcome is going to be a 1 or a 0. But I don't know what it is, so I'm modeling their likelihood of that happening. I can assign a probability value to either to them being a 1 or not, based on this information. And so that would be really useful in medical realms to be able to predict someone's likelihood as kind of a risk factor there. Because if somebody is high risk, that means that maybe they should be tested for something more often. Maybe it means that they should start taking a medication early as a preventative measure. So this would be really, really helpful in those contexts.